In the last video, we saw that linear methods suffer from overfitting in case we use too complex a model. And this overfitting actually is a sign of ill-posedness of the problem. And the solution to ill-posedness is actually something called regularization. And the way we added, or the way we accomplished this regularization was by adding terms to the objective function. These terms penalize high coefficients or high parameters. So, for example, we saw that our usual loss function now becomes J is a composite loss function, which is 1 by 2 times yi minus y hat I squared, I equal to, let's say, 1 to m. This is the original plus this additional penalty term plus the penalty term, which is 1/2 times some coefficient lambda, an arbitrary coefficient, sigma wi square, with the summation, which we also call norm of w square. This is the penalty term. This is also known as the regularization term. As I told you, this term is variously called Tikhonov regularization, also called L2 regularization, also called ridge regression when applied to linear problems. Now, Tikhonov regularization is a little bit more general than this, but I'm not going to get into that immediately. But let me show you. So now, because the loss function is different, this should have a different normal equation. So recall that when we started with the pure loss function, J is half yi minus y hat I square. So this led to x transpose x w equal to x transpose y. This is without regularization. Now, within one of the earlier exercises, I had asked you, in fact, this question was kind of sitting there earlier, what happens to the case with regularization? With the extra term. So now our new J is the old J plus lambda by 2, and we can call this W transpose W. Why? Because if W is W0, W1 up till Wn, then W transpose is W0, W1 up till Wn. And as we saw in the earlier video, W transpose W will simply give you sigma of W0 square plus W1 square up till Wn square. Okay. Now remember how we calculated the normal equations. The normal equations were obtained by setting del J, del W equal to 0. Okay. So now the new del J del W is going to be the old del J del W plus del W of this term, lambda by 2 W transpose W. Now, this you might recollect from your old video. Okay. Otherwise, I would recommend that you look back at it. This gives us X transpose XW minus X transpose Y. That is what this term was. This extra thing is the same as you look at this matrix W transpose IW, and we had differentiated W transpose AW before. Okay. So this is a scalar and it's a constant. We can take that out, lambda by 2. If you go back to our previous videos, this will be I plus I transpose, okay, times W. I plus I transpose, of course, since it's an identity matrix, it's simply I. So this gives us del J del W is X transpose X plus lambda I times W minus X transpose Y equal to 0. So this tells us that X transpose X plus lambda I times W equal to X transpose Y. This is the normal equations for the regularized least square pass function. So you can use this to generate the results that I showed you in the previous case. All you need to do is put W going from 1 to 9 in case you have a ninth order polynomial, and simply change lambda values. You see, this is not very different. This becomes X transpose XW equal to X transpose Y when lambda equal to 0. So the case when lambda equal to 0 recovers the original normal equations also. So this we can call, again, the same name that I gave you. I'm going to call this Tikhonov regularized normal equations. But this is for a linear system. What happens for a nonlinear system? Let's look at that next. So when we want to find out how the same idea can be used to regularize, let's say, nonlinear equations, we apply the same trick. Okay. We say that J is once again half of sigma yi minus y hat I square plus half lambda, okay, sigma wi square, okay, or wj square, let's call it, because this summation is over data and this summation is over features, okay, or the number of degrees of polynomial that you have. Now, we need the equivalent of Gauss-Newton. Okay. Now remember, Gauss-Newton worked on delta W. It worked on delta W, and whenever when the linear equation was X transpose X W equal to X transpose Y, the corresponding Gauss-Newton was Z transpose Z delta W equal to Z transpose delta Y, which basically was D. Okay, we can call this delta Y basically Y minus Y hat. Now you can rederive the whole thing in this case, in the case with this additional term, but I'm just going to appeal to intuition just in order to save time. So similarly for Tikhonov, when you have X transpose X plus lambda I times W equal to X transpose Y, you can derive this in exactly the same way that we derived Gauss-Newton. I will save your time by not doing that. You can simply write, some of you can see this intuitively, plus lambda I delta W equal to Z transpose D. So the only change, really speaking, is this. This is the additional Tikhonov term. And what this does, again, I won't be able to show it easily in practice. This is easy to see in the linear case when we added more and more terms, but this basically stabilizes. I'll show you an example, but it won't be a very clear example. I'll show you an example in the next video for the nonlinear case. But this stabilizes Gauss-Newton. Okay. So typically, if you try Gauss-Newton for some problem, let us say, and it diverges, it's a good idea to add this Tikhonov term because it will damp it. As you can see, as you could have seen in the linear case also. So Tikhonov will damp. So this is sort of a damping term. Damps oscillations or poor convergence. Okay. So this has typically slower but stabler convergence. Okay. So sometimes when Gauss-Newton diverges, Tikhonov will actually slowly converge. It will converge. It will be slower. In many cases, when Gauss-Newton does converge, as I will show you in the next video, in many cases when Gauss-Newton converges, Tikhonov converges a little bit slower, but it is sort of the typical slow but steady. Okay, so in case you get bad answers, it's a good idea to put Tikhonov regularization there, and that will give you slightly better answers. Okay, but that's not all. There is a slightly better version of this called Levenberg-Marquardt. Now, the way Levenberg-Marquardt was originally derived, at least in at least one direction, it was not through Tikhonov, but through an entirely different argument. And I will show you that argument also now. But first, let's see Levenberg-Marquardt as if it is just a variation of Tikhonov. Okay, so let's look at this equation. Okay. So let me take an example. Let's take X is a data set and it's 6 cross 3. For example, you could have 1, 1, 1, 1, 1, and there are 2 features, X1, X2. Okay. So for example, a quadratic model would be a decent example of this. W is, let's say, W0, W1, W2. So this is 3 cross 1. Now, Y has to have the same number of data points, but it is only one output. So Y is Y1, Y2 up till Y6. So this is a 6 cross 1. In case this is the case, then if I look at Tikhonov regularization, X transpose X, or let's look at Gauss-Newton itself, Z transpose Z plus lambda I times delta W equal to Z transpose B. Now Z is going to have the same size as X. Okay, as you might remember, del Y had del W. So Z is going to be 6 cross 3. Z transpose is going to be a 3 cross 6. So this matrix is going to be a 3 cross 3 matrix. Lambda I simply means lambda, lambda, lambda. So you are going to have a 3 cross 3 matrix here. And the diagonal terms alone will be modified. And each of them will go to this plus lambda, the same 2 terms, same term, this plus lambda, then same 2 terms, this plus lambda. Okay, so that's what it goes to because of the addition of this lambda. Now, the question you can ask in Levenberg-Marquardt is, why not have these 3 lambdas as different? Lambda 1, lambda 2, lambda 3. Okay, so the way Levenberg-Marquardt works is, I'll show you a different justification shortly, but let's look at the first justification. So Levenberg-Marquardt is, I don't want this modification term to just have constant terms. I'm going to have slightly different terms. Now, instead of now, this will be trouble because now you have to play with 3 hyperparameters. I have to decide on lambda 1, I have to decide on lambda 2, I have to decide on lambda 3. Over time, what they found out was, let's say if Z transpose Z is, let's call this something, I'll call this P. So let's just say this is P11, P12, P13, P21, P22, P23, P31, P32, P33, and you want to add the modification term, the lambda term. So a good idea seems to be multiply by a lambda, but multiply only on the diagonal terms. That's still true. So these terms are still 0. You are not adding anything here. But instead of adding 1 here, which was Tikhonov, you add P11, P22, P33. Okay, so there are numerical reasons for this. So basically, if it was this before, it goes to P11 plus lambda P11, P12, P13, P21, P22 plus lambda P22, P23, then P31, P32, and P33 plus lambda P33. This is the Levenberg-Marquardt algorithm. Yes. So the idea is simple. You see again that in effect, what you have done is you have added 3 different terms. Earlier, you were only adding lambda. Now lambda is scaled according to what the original term was. That is the only idea. It can be seen basically as a modification of the Tikhonov algorithm. So you can write Levenberg-Marquardt as Z transpose Z plus lambda times diagonal of Z transpose Z. So only the diagonal terms get added. That is this term. This is basically diagonal of Z transpose Z multiplying delta W equal to Z transpose times delta Y, which we called D. Okay. So compare this with Tikhonov, which is Z transpose Z plus lambda times, this is diagonal. You can see it as diagonal of just 1, 1, 1. Okay, so that's the only change. So Levenberg-Marquardt is less stable than Tikhonov, but faster. So this is the standard algorithm for nonlinear inverse problems. Okay, so for nonlinear regression, this is the standard algorithm and it works pretty well. Now I want to give you an alternate interpretation. As I said, there are multiple interpretations of both these algorithms. So the alternate interpretation of the LM algorithm it's like this. Okay. So suppose I again look at this Z transpose Z plus lambda times diagonal. Or actually, let me give an alternate interpretation of the Tikhonov version itself. Okay, of Tikhonov algorithm, because it's a little bit easier to see there. Okay. So lambda times I times delta W equal to Z transpose D. Okay. And instead of calling it Z transpose D, I'm going to call it Z transpose Y minus Y hat. All right. Now what happens when lambda is very high? Okay, so imagine lambda is very high. Then this becomes lambda I delta W equal to Z transpose Y minus Y hat. Which means delta W equal to 1 by lambda Z transpose Y minus Y hat. All right. Now let's call this something. Let's call 1 by lambda as beta. Z transpose times this we know is negative of del J del Y hat. Okay. This we know is del Y hat del Y. So basically you get delta W. I can show it in a matrix term, but I'm kind of running through this a little bit faster than you might be comfortable with, because I'm just trying to show a particular point rather than do some mathematical derivation. So this basically says, so all these matrices, you have to be a little bit careful about transposes, etc. I'm not being careful. This is not a formal derivation, but I want you to see this. Del J del Y hat del W is the same as saying del J del W. So this is gradient descent. Okay, so notice, remember that delta W for gradient descent was minus alpha times del J del W. So all we have is gradient descent with alpha equal to 1 by lambda. Now, what does this mean? When lambda is very high, alpha is very low. Okay, so it is exactly corresponding to that. So if I keep the regularization parameter, or what looks like the regularization parameter, as very high, what Tikhonov regularization does is it just does gradient descent. Okay, many people call this version of Tikhonov also as Levenberg-Marquardt, which is not quite accurate, but that's okay. I mean, different names are sitting in the literature. So this at high alpha or high lambda, Levenberg-Marquardt or Tikhonov is equal to gradient descent. Now, what happens at low lambda? At low lambda, this becomes Z transpose Z delta W equal to Z transpose D, which is Gauss-Newton. So another interpretation of Tikhonov is a blending of Gauss-Newton with gradient descent using lambda. So high lambda gives me gradient descent, low lambda gives me Gauss-Newton algorithm, and this is a nice way of seeing Tikhonov. So this puts us right in between. Now, what happens when you use gradient descent is it is less accurate, okay, but better behaved. This is more accurate, but less stable. Okay. Now, what you want to do ultimately is something else. So we usually have something called a lambda schedule. That is, change lambda as iterations go on. So initially, we use high lambda. This is called a schedule. And later on, use low lambda. Okay, we are not going to do any such thing. Typically, what will happen is you will start with, let's say, lambda equal to 1. Then after a few iterations, you make it 0.5, 0.25, so on and so forth. And as it comes closer and closer to the actual answer, you get closer and closer to Gauss-Newton, which will converge very, very fast. Initially, you want to explore a lot of the parameter space, and as you come later on, you come to better and better accuracy as you come to the parameters. So what we saw within this video were these two variants of regularization, Tikhonov as well as Levenberg-Marquardt. In the next video, we will look at a simple coding example with the same case that we did for Gauss-Newton, the unsteady conduction, unsteady convection plus heat generation case, which was a nonlinear case. And we'll see how you can write the program for this. You'll see that the variations are actually quite small. And I have a few comments about performance of these algorithms also in the next video. So see you in the next video. Thank you.